So let's start off with the definition of an isomer. So these are molecules with the same molecular formula but a different structural or spatial arrangement. Structural arrangement means that essentially the atoms are moving in different positions across the molecule. A spatial arrangement may be that it's just pointing in a different area of space. Now sometimes the best way to kind of visualize this is to look at an example. Now a specific example, or a very common example, is C3H6O. Now at this point you can try and draw as many different molecules which has that molecular formula. And that's something you can do. You can pause the video and give it a go and see how many different structures you can draw. But this is actually quite a common example and you probably will have done this before. So hopefully you've had a chance to draw some of those molecules. Essentially you should come up with these two molecules you can see here and here. You should recognize that the functional group for this one is a ketone and this one is an aldehyde. I've used skeletal formula here because you should be able to recognize skeletal formula at this stage. If not, it's worth going back and having a look at those videos. Now you can see that 1 carbon, 2 carbons, 3 carbons, and the same thing here, 3 carbons. This carbon has 3 hydrogens, so that's my 6 hydrogens and my 1 oxygen. This carbon in the center has no hydrogens on it because it already has its 4 covalent bonds. Whereas on the aldehyde, I've got 1 carbon with 3 hydrogens, so that's 3, 1 carbon with 2 hydrogens, so that's another 2, 5, and this carbon here has 3 covalent bonds we can see coming off this point, but that means there must be a hydrogen also coming off that, and sometimes we do see when it comes to aldehydes is a hydrogen drawn off like so, but that's not always shown. So a good opportunity to be really aware of that point there. So like I said, these are classic examples of isomers. Now something I'll look at a little later on is I call these functional group pairs when it comes to isomers, ketones and aldehydes. This is actually a type of a functional group isomer which we'll look at shortly, and it comes under the main branch of structural isomers. So there are 2 types of families, if you like, of isomers: structural isomers and stereoisomers. So here are our 2 types, structural and stereoisomers. They're both written there. Now they come under the whole family of isomers, if you like. So I could show this in a family tree like so, and you can see that under the main kind of families, isomers, and you've got your structural isomers, and you've got geometric isomers, and underneath the structural isomers you've got 3 types of, or 3 smaller groups of isomers: chain, positional and functional. So position isomers, chain isomers and functional isomers, or functional group isomers you could also call it. And on the other side you've got geometric, and actually that should stay stereoisomers, so let me change that. There we go. So stereoisomers, and underneath stereoisomers we have geometric and optical. Now optical isomers tends to be looked at in year 2, and that's when you'll probably look at that in a lot more detail, and we'll look at this in later videos. Now in regards to structural, remember this means a different arrangement of atoms, so we can pop that in there. So we have a different arrangement of atoms, so a different arrangement of atoms within the molecule, and stereoisomers means a different spatial arrangement, which basically means that it could be pointing up, down, in just a different direction, but it will still be attached to the same atom. So different spatial arrangement. Okay, now we're going to focus in this video on chain, position and functional, and then we'll later look at geometric. And geometric isomerism only occurs with unsaturated compounds. So let's have a look at structural isomers. Now, structural isomers is something about the structure changes, i.e., as I've mentioned, the atoms change positions. So that's structural isomers, something about the structure changes, atom change positions or changes positions. And we have three types: chain, positional, and functional group isomers. And we're going to look at examples of each of these. So to start off with, let's look at chains, probably the most easiest one to look at. Now, chain basically means that the chain length changes. So a good way of deducing whether something is a chain isomer of another substance is looking at the root name of the molecule. So that could mean that it changes from a pent to a bute, or a bute to a prop, or a bute to an oct, because it becomes less branched. Now, branching is a very key kind of bit of evidence to say that, oh, this is a potential chain isomer. So an example of that, and a simple example, would be as follows. So this is a molecule which is 4 carbons long, so we know that is going to be bute. So if we just write the root name is going to be bute, you should be able to name this molecule because it's a saturated alkane, or hydrocarbon, saturated hydrocarbon I should say, hence an alkane, so it's butane. Now, if I start to branch this molecule, so what I might do is I'll take this part of the molecule, so the CH3, and I kind of decide to put it in the middle here and branch it off. I end up with something like this. And what you get here is, now that, well, you get a prop chain, so the chain length has changed. So it's gone from 4 carbons to 3 carbons. So this is prop. So that kind of highlights the fact that, okay, the chain length has overall changed. Still got the same number of carbons, it's just that we've taken one of those carbons and we put it in the middle. So there's still 4 carbons here. The formula is still C4H10. That's no different to butane, but the longest chain length, the longest continuous chain length is prop. So yeah, it's propane, but this time it's branched, so it's on the second carbon, the methyl group, so it's 2-methyl propane. So this is a chain isomer because the chain length has changed. Now, when we're trying to identify what type of isomer it is, positional, functional group, or chain, always ask yourself the question, what has changed in the molecule? So moving on to positional. So I've got a molecule here that you might want to name. Now, as it says on the tin, positional, something changes position. So it's always worth looking at the name of molecules to begin with. The best way to describe this is when a functional group isomer, a functional group changes its position somewhere along the chain. So the chain length essentially stays the same, but functional group changes position. Now, the functional group here is, we've got an alkane and we've got these alkyl groups. The alkyl groups I may just highlight just for ease of view. These are my alkyl groups. They're branch chains off the main chain. Their positions will essentially change. Let's get rid of those. Right, so let's first have a look at the name. I'll just quickly do some naming. So our longest chain length is 1, 2, 3, 4, 5, or I could have gone down here. I could have said 5 like that. I just decided to go up. So it's 5. So the root name is pent. So let's write that down. So we've got pent. Now we need to give our functional group here, alkyl groups, the lowest priority numbers. The lowest priority numbers will be as follows. So if we just go 1, 2, 3, 4, 5, 6. I could go 1, 2, 3 and so on the other way, but that will give these two alkyl groups too high a number, whereas I could just give it number 2. So I'm going to stick to this numbering system here. So this is a pentane molecule. I've got 2 methyl groups, 1, 2, so it's dimethyl. So always remember to say how many you have. So that's methyl, dimethyl, di meaning 2, and you need to tell me where they are. So I'll just pop this in a different color. Now both of them are on the 2 position, the second carbon, so I need to say 2, 2. Okay, so hyphen between numbers and letters and commas between numbers when naming. So that's the name of this molecule. You can pause the video at this point and try and draw a positional isomer of this molecule and see what you get. There will be a few options here. You're not just constrained to one answer, but you can pause it and see how you go at this point. So hopefully I've had an opportunity to draw some of these. There'll be more than one, like I said. I've just drawn the main backbone of this, so it's still a pentane, but I'm going to move that methyl group around, and I'm going to do that in a different color. So I could keep one here at this point, so on the second carbon, and I can move it there. This molecule here would then have a name of 2,3-dimethyl pentane. Okay, so there's nothing wrong with that at all. Let's go and have a look at some other options. So I can move the second methyl on the second carbon to another position as well. So I could have one on the third and one on the fourth, which turns this into 3,4-dimethyl pentane. Okay, I could then say, right, you know what, I want to put them both on the third carbon, like so, and that turns this into 3,3-dimethyl pentane. So they're both on the third carbon here. I could also have 2,4-dimethyl pentane, which is this here. Now, just for as an example, there are some, these are the do's if you like, there are some don'ts. So I just want to kind of review those, and this is common mistakes that students make, thinking they've created something new, but they haven't. So let's do that. So I've put another backbone here of pentane. Some students think, right, okay, what I'll do is I shall leave, it doesn't matter where this methyl group goes, so let me get rid of that, do it in a straight line. But they tend to think, oh, okay, well, I'll move the other methyl to the end, at the end of a carbon, or I could have done it equally on this side as well. But what that does is that makes it a chain isomer as well, because you're changing the chain length. So instead of pentane, this becomes hexane, so it becomes a chain isomer. So it's really, really important that you don't end up sticking a carbon at the end if you're trying to make positional isomers, and just be careful so that you don't have two of the same. We also have students, if we look at this, so if we look at this one here, we have students that decide that this molecule and this molecule, so these two molecules are completely different to each other, whereas in fact they're entirely the same. There is nothing different about these two. They are both 2,3-dimethyl pentane. It's just that you're looking from it from a different perspective. That's all you're doing. So it's definitely worth mentioning that, you know, these two here and here are the same. They are not different at all. In fact, let's write that down just there. So they're completely identical to each other. Last but of course by no means least, functional group isomers. Now, functional group isomers is when you move the atoms around in the molecule, and that results in a different functional group entirely. So you have the same molecular formula but a different functional group. So moving atoms around the molecule cause it to have different functional groups. So again, ask yourself what's changing. Same molecular formula, different functional group, so it's got to be a functional group isomer. Now we've already seen one above, the aldehydes and ketones, and they are what we call, well, what I call functional group pairings, and it's worth knowing some functional group pairings. So functional group pairs, I'm just going to put that in inverted commas, just something I say generally. So first of all, we've got aldehydes and ketones. That's when you move the atoms around and you end up with a different functional group. You've got carboxylic acid and esters, which an example of that would be as follows. So if I draw carboxylic acid, simple carboxylic acid, there we go. That's the Q group at the end, so OH. And oxygen bond. What I'm going to do is I'm going to move these atoms around, and I end up getting, so this is 4 carbons long, so I might go 1, change it like so, 2, 3 and 4, and then what I end up with is that. This is an ester. This is a carboxylic acid on the left and ester on the right, I should say. So this is a carboxylic acid, this is an ester. This carboxylic acid is butanoic acid. And the ester that we've got here, so this is the ester. What you want to do, if I just go through names very quickly on esters, is you want to look and find the primary chain. Now this is the primary chain, so the carbon at this point here is attached to both oxygens as part of the carboxylate group, if you like, and that becomes the primary chain, and the rest, this bit here, becomes the secondary chain. So that's your alkyl group, your branch. So what we say the molecule name is here is we say it is ethyl ethanoate. Okay, so these are both functional group isomers, like I mentioned. Again, just if you have a look at this bit I'm shading in, it has changed position from there to there. Okay, so that's kind of what's changed. It's kind of gone to the middle of the chain. Right, other examples of that are alcohols, and ethers. Now ethers is a very unusual one in terms of you don't really see it often, but I'll give you a couple of examples just underneath. One being, let's just have a look at ethanol. Okay, and the position of these atoms change such that it's a different functional group, that you get a dimethyl ether. Just shimmy that up a bit. So we've got our ethanol, and we've got our dimethyl, because there's 2 methyl groups, and it's an ether, so we just write ether, that's an L there. Okay, I'll just remove that. There you go, that's better. So dimethyl ether, and the reason it's dimethyl is because we have a methyl there and a methyl there, so it's dimethyl, 2 methyl groups. It could be ethyl methyl, so it's ethyl on one side, methyl on the other, so just you can keep that in mind. But it's one that students again tend to forget, that ethers are functional group isomers of alcohols. So we'll leave the functional group isomers there, and those are the 3 structural isomer groups that you need to be aware of. So chain, positional and functional groups, and you need to be able to draw the variation of isomers that you might get. So you might be asked to identify the number of isomers there are for a particular molecular formula. you need to also be able to identify whether it's one of those three, and also whether it's a stereoisomer too. So make sure you know these three, and have a go at some examples yourself to help you identify what chain and positional and functional group isomers are.